Okay, so let's continue with the discussion on using the transformer models and why they quickly became our main tool for learning from large data sets. So we introduced transformers and we discussed that self-attention basically enables this representation of the context. And then we discussed vision transformers that uses the encoder part of the transformer to do image classification for us. They can continue improving, and we didn't see a plateau like what we saw for CNNs. And the question that we are asking is basically, is there a limit for the improvement and how far we can go because of its getting to its limit? So the main discovery that was made or observed back in 2020 was the performance improvement from scaling of resources, model size, the data is not only possible, but also we can predict them, like how much will improve, which basically gave justification for going for larger models, larger data sets, and larger compute, because we know that we are going to get better performance. So what I'm talking about here is there is a mathematical law in a power law form that basically says, given three different scaling dimensions, namely model size, the dataset size in terms of the number of tokens in the dataset, and the compute budget in terms of the number of floating point operation. And the discovery is basically for each one of these dimensions, we have a power law performance improvement. And it tells us how much improvement we can expect with increasing of each one of these dimensions. This gave us a predictive planning. So if we invest this much, we will get this much improvement, which help us to allocate resources and allocate investments also. And that explains progress of, for example, GPT models. Even after the discovery of those laws, the models that came after that confirm those laws. And that gives us an empirical sense of scaling. So let's go back to the equation. For example, the loss that we observe based on some dimension is an addition of a constant, irreducible loss, something that we cannot do anything about. It's just like the entropy or the uncertainty in the data. Just the data is like that. And then a power law term, which is about the reducible loss and the gap between the model and the optimal performance. So the optimal is basically this, something that is the best performance. So the idea here is we can determine this constants empirically. For example, for language models, the exponents across each dimension is approximated like this. So for example, here we see the slowest improvement for investing in compute and the most improvement for investing in the dataset size. So what I mean is something like this. Basically, if you increase the parameter, the loss will decrease. So for example, it's something like this. If you increase the performance, this loss will decrease with this rate that is determined this way, getting closer and closer to this irreducible loss. And same for the number of tokens and the number of flops. And this remarkable finding really holds for different modalities. Those constants may change, but the power law form so far stands the test of time. So maybe the first paper that started the whole conversation is this paper by Kaplan and colleagues back in 2020. But something that I want to point out other than this general laws is there is a surprising result that larger models are also more sample efficient, meaning that larger models can squeeze more information from the examples that they are seeing, which is somehow counterintuitive. So all of these results led to the seminal paper of GPT-3, which was a massive bet on the scaling. GPT-3 has 175 billion parameters. And with all of these resources and the cost of several $1 million for its training, it confirmed that scaling law and matched the prediction. Other models that came after GPT-3, like, for example, models by DeepMind, also confirmed this observation. But things even get better that, oh, maybe we are under training this model. We can do even better. So the scaling can be even more optimal. And that's where the chinchilla models came in with this new notion of compute optimal language models. But the main, maybe the main result of this paper was connecting these different dimensions. For example, parameters and tokens should scale equally and not, for example, in one side. And another practical rule that it says that approximately 20 tokens per parameter is a good rule of thumb. So if we have more parameters, we can feed more data and learn more. So they basically came up with this parametric form that, if you remember, similar to the lecture on efficient net, it helped us to design more optimal architectures and language models and update those power law coefficients. So the take-home message somehow changed slightly from the as big as possible to compute optimal size with much more data. And Chinchilla, for example, they showed that they can achieve similar performance with much less number of parameters, but with more tokens. I mean, still we are doing power law, but in a more efficient way. And they showed that in their comparison of Chinchilla with the Gopher, which is a very large model, and Chinchilla with much less number of parameters, but more tokens in the training performs much better in a lot of benchmarks. So there are a lot of other models that came after Chinchilla, but they started using these principles that, well, we can give more tokens to smaller models and gain similar performances. So that's why you will see the ratio of token to parameters now much higher than those old models. So then you can revisit these models, for example, GPT-3, and retrain them with more tokens, and you will get better performance. And that's where you get a better and optimal GPT-3, which then requires much more number of tokens, and then you can just extrapolate to future models. There are, of course, some caveats to this story. For example, well, hey, what if these tokens are just repeated tokens and things like that, which basically means the data is not new, which I'm going to skip. But of course, these are those caveats. But the main thing here is if we can achieve the same performance with smaller model, we should do it, because then those models are cheaper during inference, and then they will be picked up more, which is the name of the game for any products. So if just to give you a sketch of why power law, we have to drill down into this type of loss that we use in the autoregressive, mainly autoregressive tasks, and that's the cross entropy. So there are resources like papers and even YouTube videos that I will reference on why that's the case.